Ada Byron was born in 1815, the only legitimate child of the famous poet Lord Byron and the mathematician Annabella Milbank. Her parents' marriage collapsed when she was only 1 month old, destroyed by her father's scandalous behavior and unstable temperament. Annabella Milbank, determined that her daughter would not inherit her father's perceived madness or romantic temperament, insisted on a rigorous mathematical education. This was extraordinarily unusual for a girl in early 19th century England, where women of aristocratic families were expected to study only music, art, and domestic skills. Ada's childhood was filled with mathematical tutors, scientific studies, and intellectual challenges that would have been reserved exclusively for boys in most families. Ada demonstrated exceptional mathematical ability from an early age, combined with a creative imagination that allowed her to see connections others missed. She studied Euclidean geometry, algebra, and astronomy under some of the finest private tutors available to wealthy families. At age 12, she became fascinated with the mechanics of flight, studying bird anatomy and designing theoretical flying machines with detailed drawings. This combination of rigorous logic and creative vision would later enable her to imagine possibilities for computing that the inventors of calculating machines themselves had not conceived. Her unusual education created a mind capable of bridging mathematics and imagination in unprecedented ways. In 1833, at age 17, Ada attended a demonstration of the difference engine, a mechanical calculator designed by Charles Babbage. Babbage was a mathematician and inventor who had spent years trying to build a machine that could perform complex mathematical calculations automatically. His difference engine used gears, wheels, and mechanical components to compute polynomial functions, eliminating human error from mathematical tables. Ada was fascinated by the machine and immediately understood its significance beyond mere calculation. She began a correspondence with Babbage that would last for the rest of her life and lead to her greatest contribution. Charles Babbage conceived an even more ambitious project called the Analytical engine, a theoretical machine far more sophisticated than the difference engine. The Analytical engine was designed with features that modern computer scientists recognize as fundamental computing concepts, including memory storage, a processor, input and output mechanisms, and the ability to be programmed with punched cards. This machine, had it been built, would have been a true computer a century before electronic computing was invented. Babbage struggled to explain the revolutionary nature of his analytical engine to a public and scientific establishment that could not grasp its potential. Few people understood that he was describing something fundamentally different from a mere calculating machine. If you want to discover more visionary pioneers whose revolutionary ideas were too advanced for their time and forgotten by history, subscribe now and activate the notification bell so you never miss these extraordinary stories of genius unrecognized. In 1842, Babbage traveled to Turin, Italy to present his analytical engine to Italian scientists. An Italian engineer named Luigi Menabrea wrote a detailed description of the engine in French for a Swiss journal. Babbage asked Ada, now Ada Lovelace after her marriage to William King, to translate Menabrea's article into English. Ada agreed but decided that a simple translation was insufficient to convey the true significance of the analytical engine. She began adding her own notes to the translation, explanatory passages that would eventually be 3 times longer than the original article. Ada's notes, labeled A through G, contained insights that went far beyond anything Babbage or Menabrea had articulated. She explained the analytical engine's operations in clear terms that demonstrated deep understanding of its mechanical principles. She described how the machine could manipulate symbols according to rules, not just perform arithmetic calculations. Most significantly, she recognized that if the analytical engine could manipulate numbers according to rules, it could manipulate any symbols represented numerically, including musical notes, letters, or images. This insight, that computers could process non-numerical information, would not be rediscovered for over a century. In Note G, Ada Lovelace included a detailed step-by-step procedure for calculating Bernoulli numbers using the analytical engine. This algorithm specified exactly how the machine should be configured, which punch cards should be used, and how variables should be stored and manipulated. The Bernoulli number algorithm is now recognized as the first computer program ever written, a complete set of instructions for a machine to perform a complex mathematical operation. Ada anticipated concepts like looping, where the machine would repeat operations multiple times, and conditional branching, where different instructions would execute based on intermediate results. These programming concepts would not be reinvented until the 20th century, when electronic computers finally made them practical. Ada's vision extended even further into territory that seemed like pure science fiction to her contemporaries. She wrote that the analytical engine might compose elaborate pieces of music, produce graphics, and be useful to science in ways not yet imagined. She stated that the engine could process any content that could be reduced to logical operations and symbolic relationships. She understood that what Babbage had designed was not a calculator but a general-purpose computing machine, a distinction that most people would not grasp for another 100 years. Her writings described the concept of a universal computer decades before Alan Turing would formalize the theoretical foundations of computation. Ada also recognized limitations that others overlooked in their enthusiasm. She wrote that the analytical engine had no pretensions to originate anything, that it could only do what humans instructed it to do through its programming. This observation anticipated debates about artificial intelligence and machine creativity that continue today. She understood that machines execute instructions without true understanding, a philosophical insight that remains central to computer science. Her balanced perspective, seeing both possibilities and limitations, demonstrated intellectual maturity beyond her years. The publication of Ada's translation with her extensive notes in 1843 received little attention from the scientific community. Most readers focused on Babbage's machine itself rather than Ada's profound insights about its implications. Some dismissed her work as the enthusiastic speculation of an amateur rather than serious mathematical analysis. The fact that she published under her initials AAL rather than her full name meant that many readers did not realize the notes were written by a woman. Had her gender been more obvious, the dismissal would likely have been even more complete. Ada Lovelace struggled throughout her adult life with health problems that limited her ability to work consistently. She suffered from respiratory illnesses, digestive disorders, and severe headaches that left her bedridden for extended periods. She attempted to continue her mathematical studies and hoped to pursue original research in neuroscience and mathematics. She corresponded with leading scientists of her era, trying to gain acceptance in scientific circles that were almost entirely closed to women. Despite her aristocratic status and famous name, her gender prevented her from attending universities or joining scientific societies. Ada also struggled with financial difficulties caused partly by a gambling addiction. She believed she could use mathematical analysis to develop a betting system for horse races. Her attempts to win money through gambling instead led to massive debts that she hid from her husband. This aspect of her life has been used by some biographers to diminish her scientific achievements, as if her personal struggles invalidated her intellectual contributions. The tendency to focus on personal failings rather than professional accomplishments has been particularly pronounced for women in scientific history. In 1852, Ada Lovelace died of uterine cancer at the age of 36, the same age her father Lord Byron had died. She was buried next to her father in the Byron family vault, despite having barely known him during her lifetime. Her mathematical work and her insights about computing were largely forgotten after her death. Charles Babbage never succeeded in building his analytical engine, and without a physical machine, Ada's programming concepts remained purely theoretical. The Industrial Revolution continued with mechanical devices and steam engines, but the computing revolution she had glimpsed would not arrive for another century. For nearly 100 years, Ada Lovelace's contributions were erased from scientific history or attributed entirely to Charles Babbage. Babbage himself was remembered as an eccentric inventor of unbuilt machines rather than as the father of computing. Ada was occasionally mentioned as Babbage's assistant or as a minor figure who helped translate documents. The significance of her notes and her algorithm were not recognized by historians of science. The computing pioneers of the 20th century rediscovered the concepts she had articulated without knowing that she had described them a century earlier. The rediscovery of Ada Lovelace began in the 1950s as computer scientists started investigating the history of their field. B versus Bowden republished her notes in 1953 in a book about faster-than-thought computing machines. Alan Turing, who had developed the theoretical foundations of computer science, referenced Lovelace's objection in his famous paper on artificial intelligence. Gradually, historians recognized that her notes demonstrated understanding of programming concepts that would not be reinvented until electronic computers made them practical. Her algorithm for Bernoulli numbers was acknowledged as the first computer program in history. In 1980, the United States Department of Defense named a new programming language Ada in her honor. The Ada language was designed for embedded systems and critical applications where reliability was essential. This official recognition from the military establishment that funds much computer science research represented belated acknowledgement of her contributions. However, many computer scientists and engineers still did not know who Ada Lovelace was or why a programming language bore her name. Her restoration to scientific history remained incomplete. The debate about Ada Lovelace's contributions has become contentious among historians and computer scientists. Some argue that she was merely Babbage's interpreter, translating his ideas into clearer language without adding original insights. Others point out that Babbage himself acknowledged that Ada understood the analytical engine better than he did in some respects. The documentary evidence shows that she articulated concepts about general-purpose computing that Babbage never explicitly stated. Her algorithm was unquestionably her own work, as Babbage confirmed in their correspondence. The tendency to minimize Ada Lovelace's contributions often reflects broader gender bias in evaluating historical figures. Male scientists whose contributions were collaborative or built heavily on others' work are not subjected to the same skeptical scrutiny. The standard of proof demanded to accept that a woman made significant intellectual contributions is often higher than that applied to men. Ada's aristocratic background and personal problems are used to suggest she was a dilettante rather than a serious thinker. This pattern of historical dismissal has affected countless women whose scientific work has been undervalued. Modern computer science recognizes Ada Lovelace as a founding figure whose vision anticipated the digital age. Her understanding that machines could manipulate symbols according to rules underlies all modern computing. Her recognition that computers could process non-numerical information predicted word processing, digital music, computer graphics, and artificial intelligence. Her algorithm demonstrated that complex procedures could be broken into discrete steps that machines could execute. Her philosophical insights about the limitations of machine intelligence remain relevant to contemporary debates. The programming concepts Ada described in 1843 are taught in every introductory computer science course today. Looping, where instructions repeat until a condition is met, is fundamental to all programming languages. Conditional execution, where different code paths are followed based on data values, enables decision-making in software. Variable storage and manipulation, tracking values that change during program execution, are essential to computational thinking. Every software developer uses these concepts daily, building on foundations that Ada Lovelace articulated. Ada Lovelace Day, celebrated annually on the second Tuesday of October, honors women in science, technology, engineering, and mathematics. The celebration recognizes that highlighting women's scientific achievements combats the historical erasure that affected Ada herself. Hundreds of events worldwide celebrate women's contributions to STEM fields on this day. The continued need for such recognition reflects the ongoing challenges women face in technical careers. Today, as we write software, program algorithms, and debate artificial intelligence, we are working with concepts that Ada Lovelace described in 1843. Every computer program running on billions of devices worldwide descends intellectually from the algorithm she wrote for a machine that was never built. The software industry worth trillions of dollars globally rests on foundations she helped establish. The digital revolution that has transformed human civilization was glimpsed by a 19th-century English woman who died at 36. Ada Lovelace's hidden genius imagined the computing age a century before it arrived, writing the first computer program for a machine that existed only on paper. Her visionary insights were dismissed during her lifetime and erased from history for decades after her death, yet her ideas proved prophetic when electronic computers finally made them real. Her story reminds us that genius can see possibilities invisible to contemporaries, and that the suppression of women's intellectual contributions has robbed humanity of recognition for countless brilliant minds whose work shaped our modern world.